Okay, so this talk is improving libp2p to scale Ethereum. Csaba's been in our community for years now. I've known you for 3 years. You predated me even.
I think so.
Okay.
But I cannot mirror the screen.
Did you? You can't mirror the screen? So if you go to settings. Yeah. System settings. Okay, then you go to display. So you can either search or go to displays. Then you click that and click that.
Extended mirror, yeah. That was my default in the past.
There you go.
Much better.
We good?
Thank you. So I'm Csaba Kudai. This is the second Insta slide. I'm working in the EF and the Go Ethereum team. Previously, I was working in Codex storage when I was working with guys from the NIM, libp2p, libp2p. Then I was working with on database sampling, scaling research, and that's where I was working with consensus clients. And now I'm working in an execution client to make the whole circle. So before going into the libp2p specific things, I just wanted to have this map of networking protocols in the current Ethereum ecosystem. Oh, thank you. We have the EL networking and we have the CL networking. And the EL and CL is connected with this engine API. And these are currently independent peer-to-peer networks with order functions. The EL responsible for sync and mempool, and the CL responsible for block diffusion, attestation, and block and DAS, basically. Now, if you look at the protocol landscape, this is what we have now. So we have disk v5, disk v4 to the left, to the right, and then we have a bunch of things over libp2p, and then we have a few things over libp2p, and between the two we have JSON RPC. So many things which are suboptimal, I would say, many things where we can work on improvements. I was saying those are all libp2p, but actually for the DAS part, blob dispersal and sampling, there are questions. So while you can map it into the current gossip sub, it's like far from being ideal, to put it like this. And also for the sampling, while there were plans to do it over libp2p, that was very inefficient, and you can just do it over UDP much more efficient. Now that there is quick, we can again resync the thing, but not everything is libp2p. Okay, so, but let's focus on libp2p. So the first topic is large message diffusion in the network. This is what we call typically block diffusion, because our blocks are large. Now the thing is that gossip sub was not meant for large messages, it's just not designed to do that. And that is seen. So this is a measurement we were doing 2 years ago on block diffusion times in the network. And at the time, the largest blocks were around that size. And what you see, so the curves that you are seeing is an approximation of the diffusion time of different size of blocks. So you have the blue curve, which is the small blocks, up to 250K. And then the next curve, which is blocks between 250 and 500K, and so on and so forth, down to 1.5 megabyte blocks. This is the complex size, so the on-network size of the blocks. And then we are measuring it from different points in the network and kind of did the statistics of a bunch of blocks. So this is not a diffusion of a single message, but this is reception time of many blocks put in brackets. And what you see is that at the end, towards 1.5 megabytes, we start to have issues. It was fine with the 4 seconds, but it's clearly not what, if you are working networking, would like to see just to send out 1.5 megabytes in the network. So yeah, it was slow, and it is still slow, but there are different ways we can make it faster, and I was trying to summarize it on this slide. And I'm not going into the details of each one of these, just speak about them. So the first thing is segmentation. If you are sending large messages, you should segment. That's how it should work. You should not send 1 megabyte messages stolen forward. If you are doing segmentation, you can also do other things. You can do structured message IDs, so the segmentation structure should be exposed. And then once you expose it, you can do things like sending bitmaps for I-halves, for I-ones, and just operate based on those. And this is something which goes into specification. Then the second tool that we have here is scheduling and prioritization. So again, if you want to do low latency, then you should, and you are bandwidth constrained, and you should think of being bandwidth constrained. Then you should think about which part I'm sending and who am I sending to. And this is scheduling and prioritization. And here we have a few techniques which we started to introduce. So one is batch publishing, which is simply about the thing that when you are sending out pieces, you are not sending out the first piece to everyone and then the second piece to everyone, but you are sending at least the first copy first, and then you think of what to do next. And then there's the peer-to-peer forwarding part and the scheduling priorities. So there you can find my write-up on push-pull-phase transition. So that's about the fact that when you are starting to push messages in the network, first there are no duplicates, basically, because you are just sending it to, you are not sending it twice to the same node, hopefully. Then these are redistributing, you might have some duplicates, and then in the last hop, you will have all the duplicates, basically. So yeah, the math behind it is the same as we heard before in Muriel's talk. So the idea here is basically you are starting to push, and then towards the end of the diffusion, you are switching into pull mode, and this way you are eliminating large parts of the duplicates. Quick transport, I'm not speaking about it. You have seen, we will have it. It has a bunch of advantages. Very important, unreliable transport mode for when we are doing read Solomon encoding at least. It's useless to resend the same segment, the same part when we can send another one. So we can use that quite a lot. Then the next one is aggregate rate control. Is something I've been working on like 10 years ago. It's about the fact that when you are doing peer-to-peer and connecting to many nodes, you have rate control in every individual link, but then you are changing this, and then you have rate control on different connections. And overall, you don't have a rate control. And you are overloading your link, and you are increasing delay. So if you want to stay low delay, then you have to control the rate of the messages as an aggregate and not peer by peer. I mean, you have to do that as well, but you need to control the aggregate output bandwidth so that you can stay low delay, you are not overloading the buffers on the network. Next one is encoding. I was staying very generic there. You can do stuff, read someone fountain codes, random linear coding, and we had talks on that, so I'm not going into detail. And then there is network coding. I'm also not speaking about that because we had a fantastic presentation on that. And finally, overlay optimizations. That's again a huge topic. The basic intuition is just why send things around back and forth over the ocean. Like we know why we are doing it maybe in anonymization, but maybe here we don't want to do it. So there are a bunch of works on that. There are also new works on that, just latency-based optimizations of the overlay topology. This is the toolbox. We are not doing anything of this now in Gossip Sub, so you can understand why we have these delays. We should do at least some of these. Okay, next topic is small messages all over. I was just calling it, also known as the attestation diffusion. So, and we are using Gossip Sub also for this. So there is the first question, why are we using Gossip Sub for this? When we are actually not want to send it to everyone. But let's put this aside and just look at what we have. So I was running a measurement, and now I was running this measurement on like kind of what are the diffusion times that we are getting with attestations. And really what you have to know about attestations is that every node is sending a message and everyone else wants to receive it. So it's everyone to everyone kind of message pattern. and we have small messages. So it's like absolutely different from the other use, and we are just using the same tool with the same parameters currently, which is kind of bad choice. So here, I cannot measure how the message is diffusing because I don't have, unfortunately, a hook into every main node, every node in the Ethereum mainnet. But this is a measurement from Ethereum mainnet 2 days ago, or 3. Having my node and getting all the attestations and timestamping when I got the attestation, plus a little bit of processing time. And every curve there that you don't see the individual curves, obviously, and there are no statistics on it. So every curve is just the times when I was receiving attestations. So for every slot, and you see the slot numbers, I'm receiving a bunch of attestations, timestamping them, and then drawing the curve. And it has this very strange shape, and there is a reason for that. Some clients are sending the attestation at 4 seconds, some are sending it before. So you have this overlap of those that were sending it before. So the left side of a curve is someone who was sending it before, it was receiving the block early, it was not CPU overloaded, and it was close to me. And if you just take one curve and take the top rightmost part of it, then you get a node which was delayed, CPU overloaded, far from me, and so on and so forth. Anyway, you can draw a curve for every slot, basically. This is very noisy. We cannot say what's the delay. So we can look at this one. This is a cleaned up version. We have the missed slots. So in the missed slots, no one is getting the block. And then they are timing out at 4 seconds. And at 4 seconds, they are sending the attestation. So at least the sending points in time are synchronized. I'm on the receiver side, I'm getting these, and then I can draw a reverse curve, basically. It's not I was sending a message and how the others received it. I managed to make everyone send a message to me, and I was receiving it. And these are the curves we are getting. Again, no statistics. It's every single curve is a single slot. And what you can see there is that kind of the bulk of these is propagating fast. In a few seconds, but there are some outliers. Again, this is here, everyone is sending to everyone. So it's, don't think of this as if I would send a message in isolation. Here there are a bunch of messages going on all over the place. This is what we have now in the system. Hopefully we will have something faster. Last topic is the large message dispersal. Is what we need for data with sampling. So I'm not having a large message and I'm sending it to everyone. I'm having a large message and everyone wants a small piece of it. And overall, I would like to prove that actually we have enough data in the network. So here we were having this design, which is based on Reed-Solomon coding and the 2D variant of it, and a bunch of techniques to make it fast. So the techniques that I was showing before for the large message are largely utilized also here. So what we are doing the 2D Reed-Solomon coding, and then we are sending it in columns and rows, and then we are fast forwarding between columns and rows, so we have multiple diffusion paths. We are decoding on rows and columns if and when we can, and then if someone is sampling, we are sending down the sample as soon as we got it. So the sampling is very fast. It works to some extent. We have simulations on it using libp2p and Shadow. What we have is kind of a naive implementation. So I was doing this, what I call the natural mapping. So this problem is mapping to gossip sub in an easy way, which is, let's say every row is a gossip subtopic. Let's say every column is a gossip subtopic, and let's just use gossip sub with small messages. It's not ideal. We have many small messages on gossip sub abused in a way that it was not meant to. It does work. It's obviously not ideal. We can get better things out of it. So there's the dispersal, and you can do it, and then there is the sampling. For the sampling, we are not using sorry, we are not using libp2p. We had a version which was using libp2p, but it's much slower than just using UDP for sampling. So, yeah. But we can go beyond this kind of simple mapping. And this is actually a slide I had in the last libp2p workshop in Bangkok. So we have these quite many cells, each one of them being 500 something kilobytes, so bytes, so nicely fitting in one IP packet. And we are doing the batch publishing. We are doing we are doing batch publishing. We are sending them cross-connecting, and then we had ideas what else we need, but it was quite difficult to get these things into the P2P at the time, also because I was changing jobs. So it's kind of stopped there, the ideas. It's still not fully evaluated. Next one. As I said, we can do incremental modifications to Gossip Sub to fit the use case better. So we can have these structured message IDs. And this is actually something which is being worked on. And it's going into specification. You can look at it as having a large message and segmenting it, or having a bunch of small messages which are forming a batch and have a structure. It's kind of the same. Obviously, it's better to look at it, I think, as a big message which is being segmented. In the implementation, we were using the many small messages which are interrelated interpretation of it. Okay, then the bitmaps I mentioned. So this is actually now a working progress specification. Marco was writing up something called partial I have, and partial I want, and there's the partial I have, which will allow us to kind of make more efficient the not sending individual messages, and especially the metadata related to the individual small cells. Finally, should it be Gossip Sub? Maybe not. So maybe it would be better to have a dedicated libp2p protocol, which is called dispersal, which is just doing that and doesn't try to be a Gossip Sub, which has a different use. Gossip Sub is a broadcast of one message. And we are just not doing that service here. Maybe we want to have a dedicated protocol which is doing the DAS service. So it's doing the dispersal and the sampling. And notice that in our construct, we have these two phases, the dispersal and the sampling. It doesn't have to be like that by definition. So maybe we can have constructs where we are doing it as a single service, more integrated. Maybe not even libp2p. I leave that just here, but yeah. Okay, I don't know how much time, but there was an update to the FUDAS write-up. So in the FUDAS, we were doing this 256 blobs to the read summon encoding, low latency techniques with cell level messaging. There is a version 2 update to this. In the meantime, we obviously realized that much of the data is already in the public mempool. The public mempool is currently is fully synchronized, so basically everyone have already the data. We wouldn't even have to sample. Later, when we are scaling, this will not be the case. The public mempool will have less data, but it will have data. So passing that information from the mempool to the CL, which is doing the DAS, is like not doing it is quite stupid. So we are doing it, and we are doing it already. This gatblobs v3 is a way of doing it better. So doing it notification based, which just makes the interaction between EL and CL better. And then I had different thoughts about how to use LLC, LLNC in this. Not defined enough, I would say. But yeah, definitely was checking what we can do there. So yeah. I would have some more slides if I have time, depending on time. So the cell level messaging. So if you are thinking of the current state of implementation of the PILDA specification, which is sending whole columns, and then the sampling is just having these columns, and then the FUDAS, there is a difference between the two. And the current implementation of PILDAS, sending the whole column, is nice until these columns are small. And these columns are actually small today because we have only a few blobs. As we are scaling the number of blobs, these columns will be big, and then we have large message diffusion problems. So we need to segment them. And when we are segmenting them, it comes with advantages. First advantage is that you have this store and forward delay problem going away. Second advantage is that you can do column reconstruction. So someone has, oh, I still have time. So someone has, because the mempool is already doesn't have the capacity, because we are scaling, to have everything, someone might have part of the blobs and someone else might have another part of the blobs. And then there's the time when the block was created. So now we know which are the blobs which actually matter. And at that point, these nodes can figure out that they can actually combine, and they have the combined information. This we currently cannot do for the simple reason of not having a message which would convey the information. So if someone has almost the full column, just one piece missing, basically it has to throw it away, because there's no message saying, just give me a part. So we are adding it now as a patch, basically. But if you are thinking of cell level messaging, if you have messages which are the individual cells, then this becomes automatic, basically. I publish that I have this, you publish that you have that, and then I can just compose what I need. Currently, we don't have row topics. So the current PILDAS system is just columns being distributed. If we would have rows, we could also do partial Azure code-based reconstruction. So why this matters? It matters because with the current design, as you scale the number of the blobs, it becomes more and more CPU intensive to reconstruct. And then more nodes just don't know if they have to do it or not have to do it. So when they do it, they do a nice big calculation, and then they are just starting to spread that information. If you have row topics, then you can just do partial, because the Azure coding is just a vector, so you can just take that part of that vector and just do on the row. And then you can send that. So you can just do partial, you can distribute the reconstruction load in the network. You still need the big nodes which have all the data to reconstruct, but they don't have to do all the work. Then if we are adding the 2D Azure coding, which we don't have in the current system, then we can do the cell level sampling, which is very nice, because then we can have nodes sampling 70 kilobyte and being okay with the fact that there was this 32 megabytes of data distributed in the network. So the sampling becomes very cheap. There the question is more like whether we have types of nodes which actually need this service. Currently in the system, we don't have nodes which actually need this service. We don't have nodes which only want to do a download 70 kilobytes just to sample. But if we will have those, this is quite important. And then finally, if we combine these two, we have the 2D Azure coding and we do the row topics, so diffusion also in that direction. Then we have what I call availability amplification, might not be the right terminology, but basically the underlying concept is that there are no cases when we are on the borderline. So what can happen in data availability is that someone was releasing just enough data, 51% in a simple model. So the simplified 1D model. 51%, the data is formally available. We could regard it as available, but basically no one knows, because everyone's sampling hits on something which is not available, and then they say it's not available. So what we do, we just don't accept that block, and that block is dropped. If we have availability amplification, which is we can reconstruct in the network, and here if we have the 2D Azure coding, we can reconstruct on rows and reconstruct on columns, which means every single node is part of the reconstruction. Then we eliminate from the network all the cases where we are between 50 and 99%, and we are either below 50 or at 100. To some extent, then there are always losses and everything, but we eliminate the part which is hard to sample. So the sampling becomes much more efficient, so the system as a whole becomes much more efficient. and we don't need any more super nodes because everyone is part of the reconstruction, and you don't have to be a super node to reconstruct. If you are downloading a column, you can reconstruct. If you are downloading a row, you can reconstruct, and the network will do the reconstruction.
Nailed it.
Thank you. Yep. 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 Yes. Yeah. Yeah, my doubt there is really whether I can be sure as my individual check that the actual data which was that I'm not tricked into just because I'm only downloading a small part, that I'm not victim of an adversarial random fake random erasure coding. Yep. Yeah, that's definitely something that we should look into, and yeah.
Do you think with 2D coding, so we'll get rid of validator custody?
No, it's not the plan here. I mean, you might get rid of that, but here it's not the plan. So here you need the validator custody because this is a kind of this two-stage design which we might get rid of. But this we have this two-stage design where we need a group of nodes to be synchronized on their interest, basically. So we need, because of the coding structure, we need the column nodes to be the column nodes, and they are exchanging between them, and they are not going out of that, because then it would be a mess. So we need those, and then they are actually doing the custody of that. And then there's the second stage. The advantage is that the second stage is very fast. And I still have to understand. I quite sure it works, but that's something I have to understand. So we have a fast second stage here because the coding is a systematic coding. So you also have the real pieces. So if my sampling is that I need this and that real piece, then you just get those without any decoding needed. So as soon as I start to distribute in the column, someone sampling from the column is just getting it, which makes the sampling basically just follow the distribution curve with one latency, one hop latency. So the sampling is very fast. Yeah, that's the advantage. There was a question there.
No, you talked about using UDP for sampling. Can you talk more about it? Like, what was your strategy, plus how it compared with quick datagrams? The strategy itself.
There was no implementation of Quick in libp2p, and I was doing this in libp2p, so I was not doing it with Quick. Like, you can do everything in UDP that you can do in Quick, by definition. We were doing it before Quick was standardized. So So it should, but Quick is actually nicely done. So I suppose with Quick we could get very close to anything we do on low UDP. And obviously you have get the advantage that you don't have to develop everything from scratch. So it's good to use it. Yep.
Just to confirm, the implementation for KDS now is like with sprite dispersal row column,
Yep.
and the encoding actually only apply for the rows.
Yeah,
It doesn't
yeah.
apply any encoding. So it actually works like one dimension one, right?
Yeah. It's the current one is one-dimensional, and what happened recently is that the actual encoding is pushed now to the sender of the actual blob. So the blob sender is already doing this one-dimensional encoding. It cannot do the two-dimensional because it's block production time when the second dimension is defined. Before the second dimension, you don't know what you have to combine with what, because no one selected which are the winning blobs. So the only thing it can do is the one-dimensional, and then the second dimensional you would have to do when block production is time, because then you select what to combine. Before that, you would just combine random stuff, which might not even get to the system. I mean, to the second stage of the system. Thank you.